Last topic in chapter 11 that I want to talk to you about is effect sizes. So what are effect sizes? It's a way of quantifying the difference between two groups. Significant tests tell us, is it better for us to believe the difference is real or is the difference non-real? When the results of the test are significant, what we're saying is the difference is real. We don't really ever know because we're not testing the population, but if our groups are representative, then whatever differences we find within our groups, we can infer that that's the same thing we would have found had we been able to test it in the population. So we're basically saying that when the differences are significant, we believe the differences are real. And when the differences are non-significant, we're basically saying that we believe the differences are not real. So, but that doesn't tell us how big the differences are. And that's why we end up measuring effect sizes, right? It's a way of standardizing the difference between the two groups. And most of the influential work done in this area was done by Jacob Cohen. All right, I want you to think of effect sizes like this. It is a ratio. There's the signal and there's the noise. So I'm going to try to illustrate that by showing you some illustrations, right? In this specific case, the signal is the difference between the two groups, right? And the noise is the standard error of the difference, or the variability, basically, within the groups. So I want you to think about it like this, all right? I want you to think of effect size in terms of signal and noise levels. So here, I have this paper. It kind of looks like a piece of sandpaper, right? But it's very, very fine. And I don't know if you could see this in your lecture notes. It looks like there's a ripple on this paper. So it's like there's a radio signal. If I were to take this paper and turn it on its side, it would look like this, right? Here's the paper, and this warping, right, within the paper is the signal. Here, because the grit of this sandpaper is very, very fine, it's easy to see the signal, right? But let's turn the noise up. Look what happens, right? When the noise, that's the grit here, right? These pixels, when these pixels are not very refined, when they're very coarse, look what's happening, right? Here's our signal, and here's noise, and now we can't tell which one is signal or which one is noise. We can't tell the difference between the two. So let me turn down the noise, right? So here I start to turn down the noise, and now maybe you can start to see something, right? So it would be like this. Here's my signal again, right? And here's my noise. You reduce the noise, and you can start to see where the signal is, but it's still too hard. So let me turn down the noise some more. Look. Now we can start to see that wave again right here, right? So again, remember, the wave is the signal, right? This grid, these pixels, that's the noise. The only way to be able to see the difference between the two groups is when the signal is a lot bigger than the noise. Then we can see the signal, right? That's what effect sizes allow us to do. It allows us to see how big of the difference is when we standardize it. So how do we do that? We use this formula here. The way I've written the formula is a little different than the way your book writes it. So I want you to notice. First of all, I ask you to take the absolute difference between the two groups, because effect sizes are usually described as positive numbers. If you don't take the absolute value, then you also tell people the direction of the effect size, which is known as the direction of the magnitude, right? We're going to take the absolute value of the difference between our two groups, the mean of group 2 and the mean of group 1. It doesn't matter which order you subtract them in, because you can take the absolute value of them. And you're going to divide it by the larger standard deviation. Jose, where does the larger standard deviation come from? It comes from the square root of the larger variance. So this is what you're gonna do. You're gonna take the effect size, right? Yeah, I'm sorry, you're gonna solve for the effect size. How? You're gonna take the absolute value of the difference between the two groups. You're gonna divide by the square root of the larger variance. All right, let's take a look at the example that I gave you a little while ago, so we can figure this out. In our previous example here, right, let me go ahead and erase this. Let's take a look. What was the variance? The variance for the first group is 5.3667, and the variance for the second group is 3.5. Which one is larger? This one. We're going to be taking the square root of this number when we solve for the effect size, all right? What does the answer going to tell us? All right, well, let's take a look at that next. This is what we're going to do. We're going to get our answer, and if our answer is between 0 and 0.2, including 0 and 0.2, this is considered a small effect size. If our answer is any number in between 0.2 and 0.5, we consider this answer a medium effect size. And lastly, if our answer is equal to a half or bigger, 0.5 and above, we consider this a large effect size. So let's do this. Right? Remember, I told you I want effect sizes to be positive. That's why we're taking the absolute value of the numerator. Let's do this. What is the effect size of the data we found in the previous example? So go ahead, taking the numbers that you got from the previous example, right, the last independent sample t-test we solved for, solve this problem. Go ahead.